multiple times this what we can say, this term. So this MPPT is nothing but that is maximum power point, maximum power point tracking. What we have to do, if I'm talking about this P versus V, right? P versus V. So the graph of this P versus V is always this type. Now, if I have a variable load, let's suppose the load is variable in nature. I have a PV panel. I have a PV panel, and what I have did, I have connected one resistance, and this is variable in nature. If this load is variable in nature, by MPP point, it is shifting all the way, right? Sometimes I would operate here, sometimes I would operate here, sometimes I may be operating here, here. But what is our objective? We have to operate at this point, right? We have to trace or track this particular point, MPP point. Because if you draw the resistance line, right? If you draw the resistance line, we have various resistance lines which are having some slope. So if I'm writing like VPV divided by VPV to IPV divided by VPV, that is equivalent to 1 by R, right? Because it is representing a conductance. So if this is representing a conductance, and I have a slope where IPV is there and VPV is there, parameters, PV parameters are there, and I have different values. Suppose this is the resistance line. So it will have certain slope. It is representing some value of PV. So let's suppose this is delta IP and some value of voltage in y-axis. Right? And it is passing, definitely it is passing through the maximum point. Right? This line is known as load line. Now, if R is variable in nature, so the value of R is changing as the load is changing. Sometimes you have 10 ohm, we may have R1 as a R2 as a 20 ohm, R3 as a 30 ohm. You could have different values of R1, R2 and R3. So sometimes line may be at this place, line may be at this place. It is not mandatory all the time it will track the MPP. Correct? If you are connecting this panel in this way, if you are connecting your panel in this way, right? So tracking of MPP point, it is very difficult. So what we have to do? Under varying insulation condition, under varying atmospheric insulation condition, I'm telling you why this MPPT is required. Number one, we can there is variation in the insulation. Number two, load can also be changed. Right? Load can also be changed. So what we will do? So that this panel can see the constant resistance from this panel can see the total resistance that is constant, and it is at MPP. As you can see, if I have this MPP curve and I have three resistances in this fashion, so the value of slope of this resistance is increasing, right? Because 1 by R naught is the slope. So if I'm going here, R naught value will be infinity. If I'm going here, R naught will be 0. 1 by R naught. So slope is increasing. So suppose infinite slope is there, R naught will be 0 because slope is 1 by R naught. So if R naught is 0, so infinity will be there, right? So the coordinates of this point would be x-axis value VOC and y-axis value 0. The coordinates of this point would be 0 voltage because at x-axis, at y-axis, this value is 0, and we have ISC. So therefore, as you can see, the slope of the load line, it is varying throughout the operation. Therefore, we need some interfacing device in between source and load. Correct? Without interfacing device, if we are connecting this controller, you need to understand why this MPPT controller is really required, whether you are talking about the charging station or whether you are talking about any power plant, solar power plant, which is installed in the field, right? So the main circuit that will look like this way. We have this solar, and then we can go with the interfacing device. Interfacing device. That is nothing but DC-DC converter. DC-DC converter. And to this DC-DC converter, we are providing some duty ratio. You are providing some duty ratio D. Correct? And then this RT, the total resistance seen by this PV panel, that would be constant. So we'll have only one load line, right? There is no other load line curve. And then you can have the variable resistance at the output side. So if I draw this characteristic, right? Suppose this is the PV characteristic, you will have only one line which is operating, and the maximum power point will be tracked for this IPV and VP. This is the VM voltage where we have VMP, I would say, and this is the IMP current. So this DC-DC converter, DC-DC converter are required to perform the MPPT. Right? DC-DC converter is required to perform the MPPT. Next. So without DC-DC converter, so DC-DC converter is nothing but it is a controller. It is a controller which is required to perform the MPPT. Correct? So you will find out, as the load is varying throughout the day. How the load is varying? We have this curve. So this is drawn for 24 hours, suppose. Right? So out of 24 hours, here you can find the magnitude of power. But suppose in afternoon the peak is there, and a large number of vehicles are there. Large number of vehicles for the charging, it is available at the charging station at this point. However, suppose in this point there is no vehicle for the charging due to the solar power. There is no vehicle which is available for charging. So this way we are defining the different loading condition, but this under dynamic loading condition we should not lose the generation from this panel, right? We should not lose the generation from the PV panel. Correct? So that is the main idea. If load is changing throughout the day, that is fine. But it is not like that if load is changing, so you will get only that purpose. Now, the question is, what are the types of converters which are available for this DC-DC or to do the MPPT? Right? So we have two types of converters, right? DC-DC converters. Two types of converter. Number one, that is non-isolated. Number two, isolated converters. So under non-isolated converter, can you tell me what are the type of non-isolated converters which are there? Under non-isolated category, we have buck converter. Number one. Number two, boost converter. Third one. I hope I have given the mic access. If you have any doubt, you can unmute yourself and you can ask the question. Right? Buck converter. Yes, mic access.
What is isolated and non-isolated? What is the difference?
Yeah, so I'm telling you the difference. Non-isolated means isolation we are not providing. There is no any primary and secondary windings like high frequency transformer we are not using in non-isolated converters. So we have buck converter, boost converter, and third one, buck boost. I'll tell you both the converter, the operation of both the converter I'll tell you here. And then the third one is buck boost converter. Buck boost converter. Now, under category of isolated converters, isolated DC-DC converters, I would say, have various, and the very famous one, that is flyback converter, forward converter.
Sir, opto converter, sir.
What is?
Opto coupler comes, sir.
Optocoupler? Optocoupler, we are not talking about the optocoupler here. We are talking about the converters. optocoupler, it is used for isolation in low power circuit. Here we are talking about the power circuit 10 kilowatt, 20 kilowatt. But up to 100 watt, you are using 100 or even the lower than the 100, 20, 30 watt optocoupler. Suppose we want to isolate this power circuit from the control circuit, right? Because in control circuit you are using microcontroller. So this microcontroller, it is utilized to initiate the signal, switching signals for the voltage source converter or for this DC-DC converter. So opto isolation, that is required in control circuit. That is a different thing. Here we are talking about the power circuit. Here we are not talking about the control circuit isolation. I'll tell you both. We will discuss one category from the non-isolated converters and one category from the isolated converter. Don't worry. Right. So first, let's discuss one of the converter which is widely utilized in case of PV applications, in PV-based charging station. PV-based charging station. Can you tell me which particular converter it is very much preferred? That is boost converter. For MPPT purpose here. So what is the structure of boost converter? We have this switch, because we have to study this boost converter as, and then output side we can also connect one capacitor. Right? This is S. So can you tell me the operation of this boost converter? Operation of boost converter. Let's suppose case 1, when switch is on. When this S switch is on, what will be the circuit? Inductor, switch on, and then we have supply, and then this diode will be open circuit. We have capacitor and then resistance. So the current will try to flow in this path only. This is the V input or the solar input, V and P, whatever you can consider. So the current will flow in this circuit, right? We have this L. And the output side, whatever the energy stored in the capacitor, that will be supplied to the load or not. That will be supplied to the load. So when S is on, so inductor voltage, suppose the inductor voltage is VL, so VL will be equal to V input, or Vs we can write, or V input, that can be write as a L. Suppose I current is flowing, so L di by dt. L di by dt. Let's calculate this value. What is the ripple current? Delta I. So we can write di, that is equivalent to delta I. Delta I, that is integration of Vs into dt, and we can take this 1 over L. Right? So delta I, that can be calculated as a Vs, and dt, it is representing the turn on time. So we can take as a T on divided by L. Right? Or in form of L, how do I write? What is T on? How do I write T on? T on time. T on time, we will representing as a switching frequency in terms of switching frequency and inductance. Right? Switching frequency and inductance. Because this switching frequency, it is, multiple times it is representing this particular system. So delta IL, that can be written as Vs into D by Fs, where Fs is switching frequency. Switching frequency. Fs into L. Because for this particular circuit, you have some T on and T off. Right? So this is the time which is representing T on, this is representing as a T off. Means the inductor, it is charging for this value and it is discharged for this T off. It is discharged for T off. So T on can be calculated as a D by Fs. Right? We can replace it, and LB, that we can derive, that is D into Vs divided by Fs into delta I. Fs into delta. Now, the relation between output voltage and input voltage. Right? When the switch is off. When the switch is off, means S is off. S is getting 0 signal. So if S is off, then what will be the circuit? If S is off. So if S is off, we have inductor, and here V in, suppose. So Vs is equal to Vn, keep in mind. Vs is equal to Vn. So Vn, and then this switch is off, so open circuit. And then we have this capacitor voltage and this output one. So this is R naught, let's suppose, and then we have V naught voltage here. This is VL, and this would be the V naught which we are representing as a this value. So what is V input now? V input, that is distributing in VL plus V naught. Now you can calculate the value of inductance voltage, inductor voltage. So VL will be V input minus V naught. That we can write. So when this inductor is on, right? So VL, it is charging and discharging, because for some value it is charged and for some value it is discharged. So let's suppose VL on into D, so inductor is charged, VL off, so inductor is discharged for a duty cycle of 1 minus D. If it is charged for D, obviously it will be discharged, because maximum possible value of duty ratio, that is 1 minus D. 1. Right? Now you can put these two values. So we have VL on, under VL on conditions, this is equivalent to V input into D. But when it is off, so we have V input minus V naught output voltage and 1 minus D. Can you solve this? V input D plus V input minus V naught 1 minus D. Can you solve this? And let me know the ratio or the relation between input and output voltage. The relation between input and output voltage. Anyone who can tell me the ratio? So V naught, that can be written as V input divided by 1 minus D. V input divided by 1 minus D. So overall control. So this is the operation of a converter, how this is taking place. But if you see the overall control as well as the overall power circuit for this solar-based charging station, here we have PV panel, right? And from the PV panel, a small capacitor people are using as a CPV, so that whatever the voltage ripple is there due to variation in the atmospheric condition, that can be taken care by the CPV. And then we have L converter, and then this, right? And the output voltage, that is this. This is simple circuit of boost converter. Now you can connect the battery or you can connect a simple resistor load, whatever the power demand is there, that can be fulfilled by this circuit. Now the question is, how do we get the switching signal or D for this switch, right? So for this purpose, what we are doing, we are sensing the VPV, right? Voltage here, and the current at this point, IPV, current at this point. So we have VPV and we have IPV. Both are going in a MPPT control. Right? Both are going to the MPPT control. The output of MPPT control is nothing but, that is duty cycle or duty ratio, whatever you can consider. So, and this duty cycle, it is compared with the triangular wave of 10 kilohertz. 10 kilohertz, 20 kilohertz, depending on the size of this, depending on the switch rating, right? Whether the switch supporting this 10 kilohertz or it is supporting for 20 kilohertz, 30 kilohertz, like that, right? So output of this is going, so this is nothing but the PWM signal, which is going in this fashion, on, off, like that. So this is the overall diagram of a, this PV systems where we are using the boost converter controller along with the MPPT control. Now this MPPT control, there are various type of controller. Like the famous MPPT controls, you can ask, sir, what is MPPT control? So in MPPT control, we have part of an observer based, P and O based control, P and O MPPT control. The second one that is very famous, incremental conductance based MPPT, right? Some soft computing techniques people are also using, some soft computing methods like optimization methods people are also using to obtain these MPPT, right? Because see, in case of P and O, in case of incremental conductance, we have to see the response. So in case of PV array, the two responses, one is steady state response, second one is dynamic response, right? Steady state response and another one is dynamic response. These two responses are really important, right? Really important to get these two responses from this panel. Because if you see this MPP power curve, which is there due to PPV, if you take y-axis PPV and x-axis as a IPV, so there are two basic points. One is at MPPT, right, at MPP, and another point it is there at the VOC, right, or open circuit, at open circuit conditions. Now let me know which point is suitable for operation. This is the operating point. Now from operating point, so from operating point, your operating point would be at this place or at this place, or it is continuously fluctuating from point 1 to 2, then 3, and then coming back to 2 and 1, right? This response is known as steady state response. It is known as steady state response, because in this point is fluctuating in nature. Sometimes it is at position 1, sometimes it is positioned at 3. So if you draw this IPV and VPV, so IPV and VPV, these are the DC quantities, right? IPV and VPV. What is the nature of this quantity? Anyone? What is the nature of these two quantities?
IPV is current, VPV is voltage.
Yes.
Right?
These are the voltage, but they are DC quantities. Right? These are DC quantities. Means if I'm drawing this IPV or VPV, let's suppose first, VPV must be smooth. Suppose the voltage from the panel, that is 500 volt. So this 500, it should not fluctuate or it should not give the result in this fashion. It must provide the result in a constant way. Means voltage must fit. Otherwise, in result to this ripple, what you will see, the point is fluctuating continuously, or vice versa, right? If point is fluctuating at the MPP, your algorithm must be so strong so that this steady state and dynamic response can be handled by this MPPT, so that you can get one point only, one operating point. If you are getting multiple operating points or different value of operating signals, that will not help. So this is really important to cope up with this type of scenario. Right? So under steady state response, if point is fluctuating from 1 to 2 or 3, this will not work. Now, what is dynamic response? Dynamic response means if I have point at this particular my MPPT, or I have not connected any load, now I have connected the load and suddenly I have trying to supply some power to this load from this MPPT, from this PV array. So my how fast this point is reaching from, suppose this is point A and this is point B. How fast it is reaching to point B from A, that represents the dynamic response of the system. How much time it is taking to track this MPPT. I'm able to get it. So dynamic response, how much time it is tracking the MPP point. How much time it is taking to track the MPP. Able to get it. So this way, this will define. So some algorithm, they have very quick response. As soon as you will turn on, this point will be immediately, it will go here, and they will track this MPPT. Right? So that's all for today. If you have any question, you can ask. Otherwise, I will stop here, and I will see you in next coming classes whenever it will end. Any questions which we wanted to ask here? No question? Everyone had dinner and went to the bed? Huh? Everyone slept in the morning?
Yes, sir.
Yeah. Okay, so thank you very much for attending today's lecture, and see you in the coming classes.
Thank you, sir.
Thank you, sir. Thank you.
Thank you so much.
Thank you, sir.
Yeah. Good night, all of you.